Well, I was going to tell you about the secret life of not a number, but I think I put up the wrong talk. Just give me a minute. Hold on. This was for another conference. All right, sorry, starting over. So I'm Annie. I'm going to be telling you about the secret life of not a number. So I was working on a project where I had to think about some of the details of floating point arithmetic, and so I thought maybe I should read the floating point standard. And the floating point standard is really great. It took almost a decade to write it. The first edition was in 1985. And it's like 70 pages long, and I thought, hey, you know, if I read this, probably somewhere in these 70 pages, I'll find some like really interesting, juicy detail, and it'll be really awesome, and I'll be enlightened. And so I sat down and I read these 70 pages, and they were really boring. And I thought, somewhere in there, actually, probably there is something interesting. I probably just missed it, so I read it again. And it was just, it's so dry and so technical. It was really boring. But I didn't give up. I read it a third time, and I know that's like the fairy tale trope that you have to do something 3 times, but honest to God, I actually read it 3 times, and on the 3rd time, this paragraph caught my attention, and it says that not a number should, by means left to the implementer's discretion, afford retrospective diagnostic information. And I thought, diagnostic information? What kind of diagnostic information? And does anybody actually do this? This sounds kind of cool. So that's the story of this talk, but before I get into that, I'm going to give you a very quick overview of what floating point is and how it works. So the floating point standard defines how to encode some subset of the real or rational numbers into some fixed bit width. So this is a visualization of the precisely representable points in 16 bits. So when we have 16 bits to work with, this is how it works. We get 1 bit to represent the sign. We spend 5 bits to specify an order of magnitude away from 0. And then we use all the rest of the bits to specify where within that order of magnitude our point is. So we have these 16 bits. If we assign some kind of Boolean values, we get numbers out. And like, look, we get plus 0 and minus 0. That's kind of weird. We can represent all sorts of values. That's sort of cool. But actually, that's not the whole story, because there's some bit patterns that you don't just interpret that way as rational numbers. Some bit patterns are like special reserved quantities, and one of these special reserved quantities is not a number, and actually, weirdly, there are 2 of them. So to specify not a number, here's what we do. We have some kind of sign bit. We don't really care what it is. We set all of our exponent bits to 1, and then we have 1 bit in the mantissa that's also set to 1. If it's the top one, it's a quiet NaN. If it's some other one, it's a signaling NaN. So the difference between quiet and signaling NaNs is that, so the standard recommends that signaling NaNs should be used to represent uninitialized variables. And that's because signaling NaNs are supposed to raise an exception when you touch them. So the standard doesn't say hardware or software because it's totally agnostic to that. But either way, signaling NaNs like raise a big commotion when you touch them. So maybe you want to use them for uninitialized variables so somebody doesn't accidentally use this thinking that it's an initialized variable. The standard also recommends that you use them for arithmetic-like enhancements, such as complex affine infinities. And I spent a little bit of time Googling around trying to figure out what that means, and I actually have no idea. So if anybody knows, please come talk to me. I would love to know. So that's what signaling NaNs are for. And then quiet NaNs are just your garden variety, like something went wrong, you took the square root of a negative number, and like the square root of a negative number, it's not a number. So it's that kind of number. It's some kind of invalid operation exception. And this quote that I was interested in actually has to do with quiet NaNs, so those are the ones we're going to look at going forward. So these quiet NaNs, like I said, the top bit is 1, but all these other bits, they can be whatever they want. And that's called the payload. So we can sort of put something in there. But in 2019, we don't just have 16 bits to work with. All of our computers actually use 64 bits, which means that we have 51 bits of payload to work with. And that's really a lot of space. Like, I'm not sure what I want to put in there, but I have a lot of room to put a lot of something in there. And like what kind of something? Cats maybe out of diagnostic information? What kind of diagnostic information? And does anybody actually do this? Well, yes, they do, in fact. So I'm going to tell you, I tried to find like any use cases for this when I learned about this, but this is the best use case that I found. And it's in this JavaScript interpreter called JavaScriptCore, which is at the heart of Safari, and it's this technique called NaN-boxing. And this technique isn't unique to JavaScriptCore. The super cool JavaScript interpreter inside of Firefox called SpiderMonkey uses 2 variants of this technique under the names NaN-boxing and punboxing, and LuaJIT also uses it under the name NaN tagging. So this is the problem that NaN-boxing is trying to solve. So JavaScript is a dynamically typed language, which means we've got some kind of values that are hanging out at runtime. And we really need to keep track of what the types of these values are, because like maybe we want to try to like add two integers together, but we should really be checking the type tag to make sure that we're actually adding integers together, because things can change type dynamically, and we want to have our programs make sense. So we need to keep track of this type information, and like we could just allocate an extra 64 bits to keep track of it, but like as the JavaScript interpreter, that sort of bums me out, because like first of all, I have to use more memory, and that's like I really don't want to be doing that if I can avoid it. But then because it's in its own word, and I'm going to have to do these checks all the time, I'm going to have to be reading this into its own register, which can create register pressure, which might lead to performance issues. But if only there was a better way. But now that I think about it, we do have those 51 bits of payload to work with, and I know we're supposed to use it for diagnostic information, and this isn't like diagnostic information, but maybe it's like diagnostic information. And like all I know is I have all this room to put stuff, and I have all these things that I now need to put somewhere. And like this probably isn't a very good idea. It's sort of hacky, but maybe it'll work. So here's how NaN-boxing works. So we get 64 bits in, and what we do is first we check the bit pattern, and we say, hey, is this a real floating point number, like those patterns that I showed you for like plus and minus 0 and negative 0.3 or whatever? If it is, then it's a valid floating point number, and we can get on with our lives. Everything's great. And if it's not, then it's some kind of not a number. And like we saw before, not a number is sort of just like this box that has this payload that we can shove other things into. So if it's not a number, then what we do is we check the payload, and specifically we're going to check the payload for a type tag. And what a type tag is basically I'm just going to make a lookup table where I say, okay, what I'm going to want to put in here is I'm going to want to put in booleans, and I'll just say that that's a 0 if it's a boolean, and I'll say it's 1 if it's an integer and 2 if it's a pointer. So then I can use the type tag to interpret the data in the rest of the payload correctly to know what kind of data it is, and then I can get on with my day. So it's like I have this box, and then I can just check what's inside of it. So that's sort of what NaN-boxing is. It's this ability to like hide other data inside this extra space that we happen to have. That all sounds great, but is this actually going to work in practice? Because we have 51 bits to work with, in 2019 at least, and how much stuff do we even need to represent? Well, it turns out that actually this is just about it. So doubles I'm not worried about, because this is a normal floating point number case. And then there's a class of data that I'm going to call bools and undefined and it's sort of like there are a couple of data types that the interpreter cares about that only have like 1 or 2 instances. They're small, they'll fit, it's not really a problem, I'm not worried about it. The two, I think, interesting cases are pointers and integers. So how big are pointers? Well, today they are 48 bits, and we have 51 bits to work with. We might want to reserve a little bit of space for the tags or do something else clever with the tags, but like this seems like it's actually going to work. If pointers eventually get larger, this might be a problem, but today it seems like pointers are going to fit. So how about integers? Well, first of all, are there even integers in JavaScript? And the answer is, well, so the standard, the ECMAScript standard says, no, there are only numbers, and so everything's a floating point number. But in the real world, we write for loops, and we have like index variables that will go through and index into an array. And in reality, what we're doing is we're doing integer addition. And your interpreter really wants to know that this is actually integer addition, because floating point pipelines are really complicated, which means they're slow. And integer pipelines are much simpler, which means it's a lot faster to do integer addition. And the good thing is that if the use case is indexing into an array like this, the ECMAScript standard says that arrays can only have 2 to the 32 elements, which is like probably more than you'd ever want to have anyway, but these integers basically only need to be 32 bits wide, and again, we have 51 bits to work with. It looks like this is going to work. So the cool thing about this is this hack actually works in practice, and like this is all we had to do to make this hack work, and it actually works. The other cool thing is that JavaScriptCore and SpiderMonkey as well are both open source, so you can go and read the code yourself and figure out how does this like weird bit-level hacking trick actually work. But I'm not going to subject you to reading bit-level C++ code in the last minute of my talk. But instead, I'm just going to show you, I chose JavaScriptCore because they have this really awesome big comment that explains the scheme that they use. So I'm just going to show you this comment really quick so you can see that it's actually all the things we talked about. So these are the encodings that they use. Doubles take up most of the available bit range. And then they have a pointer type. So these are 48-bit pointers that we talked about. And then integers, these are 32-bit integers. And then the entire scheme looks like this. And the values at the top are these undefined and Boolean and et cetera values. So it all fits. It all works. So just a quick recap. The floating point standard defines ways to talk about floating point numbers, but also ways to talk about things that are not floating point numbers. And the NaN numbers, for some reason, have this very large payload that we can conveniently place diagnostic information into. And we can also sort of hack it and use non-diagnostic information in there as well. And this is actually used in practice in this technique called NaN-boxing. So it's sort of cool that it works. That's it.